Test. Okay, can you hear me? For people online, can you hear me? Thank you. All right, good evening, and let's get started. So let's continue on a double integral. So today we're going to look at examples. Okay, so because at the end of the previous lecture, we have gone through the idea of how to scan through the region R. Okay. To calculate the double integral means you are going to integrate certain function over a given region R. And the key at here, okay, so the key, integrate over something, meaning you had to scan through this region. Right? Single integral, you scan through the given range A to B. Double integral, right? The key is to scan through region R. Right? So region R is over here, and then you have certain function on the top. All right, so let's take a look at a few examples and see how the scanning works. Okay, let's say we have this simple surface, which is a plane. Region R is bounded by three things: y equal to x, x equal to 1, and x-axis. So often in time, in this case, we don't need to sketch the 3D, you don't need to sketch the surface at all, but sketching the region R is pretty necessary. Okay. So you can sketch each one of the boundaries. This is y equal to x, then x equal to 1, and then x-axis, which is here. So basically, you have this triangle here, right, as the region R, its boundary. Yes, because the next step is to get integral limits. So with the knowledge of the region R, right, then you can find limits much easier. Label each one of the boundaries if necessary, because you need the information to find the integral limits. So let's go through the scanning process, right? First step, what's the order of integration? Basically, do you want to do x first or do you want to do the y first? Right? So it really doesn't matter. Let's say we choose, in this case, okay, so we'll choose dy dx, okay, as the order. So that means you're going to integrate over the y variable first. The order right here determines how you're going to find the limits, right? So y limit. Here's how you find the y limit. You draw an arrow lines in the positive y-axis direction. Your first contact give you y mean. Second contact give you y max. So y mean is the first contact, and y max is the second contact. Obviously, the first contact doesn't really matter where you sketch this arrow line. You can sketch it here, here, okay, as long as it crosses the region R. The first contact always 0, right? Because it's always at the bottom of the boundary there. And second contact always fall onto the straight line y equal to x. So y max is x. So this is how you find the y limits. And then x limit, meaning you're going to move or scan this arrow line from the left to the right and find the two edges based on the given region R. Where the locations of the two edges will determine your x mean and x max. So obviously one edge is over here, the x mean is 0, and the other edge is on this side here, which is 1. So that gives you the limits for the x and y. So finally, we can write down the layout of the double integral. So you're integrating 3 minus x minus y. The order is dy first, and then dx. Plugging the limits for the integral is 0 to x and 0 to 1. So now you're ready to calculate this double integral from inside and to the outside. Okay, so this is a very straightforward integral here. There's really nothing tricky. The result of the calculation will be 1. So this is based on order dy dx. Okay. Now, if we do dx dy, so then you can easily change the limits by following through the same process. So then in this case, you're going to draw an arrow line, right, in the x-axis direction first. First contact give you x mean, second contact give you x max. So x mean is y, x max is 1. Then you move or you scan these arrow lines from the bottom to the top, find the two edges, sandwiching this region R. That'll give you the y mean and y max, which is 0 to 1. So this way you will get the same answer as the previous one, right? So which is 1. So this is the simple process you can use to scan through the region R. Okay, and this is actually for Cartesian coordinates. Okay, so as the way you're scanning here, as we said, we're not creating any redundancy. We're uniquely go through this region R to find the limits, right, for the double integral. Okay, let's take a look at one more example. Let's say we have a region R defined by the boundaries given at here, and then you have the top surface Z, which is y minus x squared minus y squared. So as we said, it's always helpful to sketch the region R, so then you can follow the process to find the limits. X squared plus y squared less than 1 or equal to 1 give you a circle. But then the x and y are restricted to positive number. So basically, you are restricted to just 1/4 of the circle here, right, in the first quadrant, because that's where x is more than 0, y is more than 0. So this is your region R, and with the radius 1. So once you get the R, then we're integrating this function, and then you decide, okay, so what order of integration should I take? Okay, so let's do dy ds again. Okay. And then the next step is to find the limits for the integrals. Okay. So if the order is dy dx, okay, so then I'm going to draw parallel arrow lines in the positive y-axis direction. First contact give me y mean, because y mean is 0. Second contact, and that's on the circle. Okay, so that give me the y max. So the circle equation is x squared plus y squared equal to 1. So for this part of the circle, y equal to square root 1 minus x squared. Okay. So your y max is 1 minus x squared. Okay. Then you scan through this whole region R by moving this arrow line from left to the right and find the limits for the two edges. And one is 0, the other is 1. So that's your x limits. Okay. So so far so good, right? Nothing really special. So now you carry out the integral right here. So let's carry out from inside to the outside. So first calculate the integral of the inside integral. So this one here. Now when you do this integral, you're treating x as a constant. Okay, so you get y minus x squared y minus 1/3 y cubed, and then plug in the limits. Okay. So let's take a look at what do we get. Okay. So our limit is 0 to 1 square root of 1 minus x squared. So y here, so you end up with just a square root, okay, of 1 minus x squared. And the next one, you can have x squared times y minus x squared. And the last one, you get 1/3 because this is 1 cube. Okay, and then you plug in the y with square root of 1 minus x squared. So you get y minus x squared here, and then 3/2 and dx. The other limit is 0. So when you plug 0 into the y value here, you get a 0, right, for everything. Okay. Okay, so I think if you end up at this step here, and you're almost done with the integrals. However, unless you're a genius, then I suspect that you'll be able to finish this integral. Okay, so basically you probably get stuck at this step. If you see this kind of integral, my suggestion is just give up, don't do this anymore. Okay, yeah, don't spend any time. So my point here is we do have a better approach to solve this question. Right? So right now, everything we're doing, okay, is under this Cartesian coordinates. Okay. And bottom line is, in my exam questions, I will never give you kind of integral questions like this. Okay, that's not the point for this class. Right? So if you see something like this, there's something must be wrong, right? Yeah, it's not my side. It must be something on your side is wrong, right? So the question here is, we do have alternative, right? If I don't want to go down this path, then what other options do we have? Right? This is the next topic, leading to the next topic at here, is to use polar coordinates. Okay. So basically, we're going to look at calculating a double integral using polar coordinates. And we'll come back to this question and we'll see how the introduction of polar coordinates will actually simplify the computation of this question. So polar coordinates, I believe you have learned already, probably in your dynamics, okay, or maybe in other course topics. As a matter of fact, I think we learned a little bit in 246, right? So here's the Cartesian coordinates, x, y. So you can describe the location of a point P with a pair of coordinates, x and a y, right? So the other option is you can describe the location of the point P using another pair of parameters. Here we can use the parameter r and theta. So you can basically using another pair of parameters describes its location. The r is defined as the distance from here to here, And theta is defined as the angle from the x-axis to where this OP line is. Right? So that's how r and theta is defined. Then what is the relationship between this x, y, and r theta? Right? First of all, r theta here basically is give you this polar coordinates. Okay. Just in contrast to the xy, which is Cartesian coordinates. And the relationship between r theta, xy is fairly straightforward. If you look at the geometry here, this is x, right? This is y. So x equal to r cosine theta, and y equal to r sine theta. Okay. So in theory, basically, your x is a function of r and theta. Your y is also a function of r theta. So that's a connection between your Cartesian and the polar coordinates. All right. So the title is to calculate certain double integral in polar coordinates instead of Cartesian coordinates. That basically means we're going to transform all of the x, y's into r and theta. Right, that's the idea. All right, so here is your original. Here's the original double integral. And you're integrating this function over this given region R. And dA at here is dx dy or dy dx. So we want to transform into polar. All right, so let's take a look at how we can transform that everything from here that in terms of x and y into in terms of r and theta. So let's look at the easy one, right? Let's look at the easy one here. So first for this f of x, y, the function, okay. I want to get rid of x, y, so that's easy. I can replace the x with r cosine theta, replace the y with r sine theta. You know, whatever the function is, you find the x, replace with r cosine, find the y, replace with r sine. Right now, the function f has nothing to do with x, y anymore. It's completely in terms of r and theta now. So that's changed. And second part is this dA here, right? So the dA. So how do we transform the dA? So dA, so let's say, for example, right? You have a region R. The way how dA is created is like this. You basically slice or you section off this R, right? Using horizontal and vertical lines. Right? You slice them off, and then you create as many small of patches as possible, right? Yeah. So each one of the patch, right, depending on how you slice it, of course, and each one of the patch has a delta x. Sorry, this is delta y. Has a delta y and a delta x, okay, on both sides of the rectangle or square. Okay. Then you get the small area, which is dA equal to dx dy. Right? That's how you get it. Right? That's how you basically dissecting this region R into small grids like this. So we should consider similar approach, okay, under polar coordinates, given the same region R. So here's what we can do. So let's say suppose you have the same region R and here. Okay. So if you look at the way in Cartesian coordinates, how we actually cutting through the region R is that we draw lines, right? We draw lines in the direction of the x and the y axis. So you draw the horizontal lines and you also draw the vertical lines. Now, polar coordinates, right, is what? Is you have a reading lines here. So you either the lines here or here or here, okay? And then you also have angle theta associated with it. So basically how you determine a point P is you draw a reading line over there and then you rotate somewhere, right, to the corresponding theta, then you nail down the actual location, right? So this R right here is basically a whole bunch of reading lines, right? You know, if you have a multiple points. So that's how we probably can sanction it. So we can draw, let's use red color. So we can draw many of those reading lines, right, out of this origin. So this is like you sketch a horizontal line in the x-axis direction. So now we draw a reading line in R direction, okay? So as a matter of fact, you could attach a unit vector in the R direction. Okay, you attach a unit vector in R direction, right, representing that's the polar, like the I hat, right, in the x-axis direction. Okay. So how about the theta, right? So the theta is basically, it's a rotating operation. So you rotate this line from here to next, to next, to next, right? So in this case, to represent a rotating, so basically what you're doing is you're gonna draw many of these centered circles, okay? So when you're going around the circle, it's like you're going around basically the theta, right? Yeah. So this way, it's like you attached a unit vector, okay, perpendicular to that unit vector ER. As you can see, if a point P at a different location, then the two unit vectors actually shift to a different location. Right? So that's the difference actually compared to the Cartesian. Cartesian coordinates, you know, the x, the I hat, j hat, right, is fixed. It's always pointing to the two directions. Okay. So this way, it's a similar analogy. You dissecting this region R, right, using this reading line and also using a whole bunch of concentric circles at here. Then you're creating a small patch like this, right? So this little patch here is very much the little patch you created under Cartesian coordinates. Okay, so let's explore that, okay, a little bit more just to examine that small patch. Okay, what would be an expression for that? So let's just focus on that one little area. So I'm going to draw, okay, two reading lines like this, and then you have like two circles like that. Okay. So this is the little patch right here. So suppose that from here to here is R. And then from here to here is delta R. So you increase the R by a little bit, delta R. And from here to here is theta. And from here to here is delta theta. So that's how you creating this small patch at here. So now let's see, what will be the area, right, for the shaded area here using all the symbols we have laid down here. Now, even though this is not technically not a rectangle, okay, but however, from a mathematical perspective, as long as you created this small patch with a very small movement or action, right, then you can approximate this as a rectangle right here. So that means the area will be just one side times the other side, right? So for one side here, this is delta R, right? So delta R is right here. And multiply by the other side. So the other side let's use this arc length. Okay, this arc length at the other side. So that arc length is r times delta theta. So that's an approximated expression for the area delta A. So basically equal to r times delta theta. This is your delta A, okay, in polar coordinates. Right. Previously, you created delta A in Cartesian, which is dx dy. And now in polar coordinates, your delta A becomes r delta theta. So if you suppose you're creating this very, very small, in an infinitesimal small differential concept, then this basically give you dA equal to r dr and d theta. Right. So now I can put things together, right? So I can transform the f into this. I transform the dA into this. Then the whole double integral, okay, becomes f r cosine theta, r sine theta, and then r dr d theta, right, over the region R. Okay. If you look at the current expression of the double integral, right, apparently there is no xy involved anymore. It's all in terms of r and theta. And it's still the same region R. So the next logic step is, what is the integral limits in terms of r and theta? Right, that's basically the idea here. So now you actually probably should ask the question, should I be worried about the order, like dx dy or dy dx as in the Cartesian coordinates? Because technically you also have a dr d theta or d theta dr, right? Yeah. So what I can say is, theoretically, you still have the option to choose the order, either dr d theta or d theta dr. But in most cases, you choose the dr d theta order will be much more naturally, okay, to do the calculation than d theta dr. Okay. So in polar coordinates, the order, I would say, is typically dr then d theta. That's what we typically will follow here. So I will demonstrate it also next is that how do we find the limits for r and how do we find the limits for theta? Okay, by using very similar concept of scanning through the region R. All right, so let's see. So let's do this by following through the steps sitting here. I'm going to use a region, the following region R as an example here. Okay, sorry. Let's first give us the limits here. Let's consider this region. Okay, there are three informations involved here. You have a circle, you have a line, and you also have y-axis. Now let's sketch this region R. Let's sketch the easy one. Sketch the y-axis, which we did. Sketch y equal to square root of 2. Okay, square root of 2, let's say label is here. So okay, so this is y equal to root 2, right? It's a straight line. And the last one, you sketch this circle, x squared plus y squared equal to 4. So the radius of this circle is 2. 2 is more than root 2, so 2 is somewhere here. This is, let's say this is root 2. You sketch the circle, right? Obviously, circle will look like this. I mean, if you keep going, then the circle will end up here, and it's also 2. But the circle will intersect this y equal to root 2. So basically, your region R is this little area. Okay. So now let's look at this question. Suppose maybe in a question given is integrate certain function over this region R. Okay. So without specifically calculating integration for certain function, right? Let's just focus on finding the limits. Now, of course, we said we're now in this case we're looking at the polar coordinates instead of the Cartesian coordinates, right? So whatever the function given, you will transform it into r and theta first. But let's just focus on the limits here. Okay, step 1. Step 1 to find r limits. To find the limits, okay, we follow the similar approach, okay, as we did for finding xy limits. Remember, when we find the xy limits for Cartesian coordinates, you first determine the order, let's say dy dx. And the next step is you draw an arrow line in the y-axis direction. In the y-axis direction, that's actually the direction of your first chosen variable y. Right? That's the first arrow line. So if I follow the same approach at here, okay, then what I need to do is, so I need to draw, okay, instead of arrow line, I need to draw a reading line from origin through region R. Okay. So you draw a reading line like this through the region R. I mean, this one here is basically in what direction? In the direction of the R direction, right? Yeah. In the you have that unit vector ER representing the R direction, right? That's why we draw here reading lines. Okay. And similarly, first contact. So first contact gives R mean, and second contact gives R max. Okay. The definition for R mean, the definition for R, right, is the distance from origin to wherever the location is. Then if this is the first contact, then R mean is distance from here to here. Right? And R max will be the distance from here to here. Okay. So apparently the first contact falls on the line y equal to root 2, and the second contact falls on the circle, which is right here. Okay. So let's deal with the easy one. So what would be the value of R max? I heard 2, right? Because it really doesn't matter where you draw it here. As long as cross region R, it falls on the circle. The distance from origin to anywhere on the circle is radius, right? So 2. Okay. So that's R max. So the R mean, right, is a tricky one. So technically, this is your R mean. However, as you can clearly see, will R mean be a constant value, right? You look at this here, so this is the current of R mean. If I draw the arrow lines over here, then this is R mean here, right? So R mean is not going to be constant. It's a changing quantity, okay? So, but how does it change, right? So we need an expression for R mean. So we cannot just put a number at it here. So we need to find an R mean expression in here. So the general idea is, right, very much like the Cartesian, when you find the limits for the y, you probably will find the limits for the y is a function of x. So then the R mean at here, or even R max in certain cases, right, could be a constant, or in general could be a function of the other variable, which is theta. Right. So, and also you had to make use of some of the available geometry relationship to find that relationship. Right. So let's say here is what we're going to use. Okay. I'm going to look at this triangle here. So look at this triangle. This is a right triangle, right? So I'm going to sketch this right triangle right here. And then label, so this side of the triangle is root 2. That's how tall it is. And then technically, right, this side is theta. So if this theta, so what's this angle? Theta, right? Good. And what are we looking for, right? We're looking for the hypotenuse, basically, which is the R mean. So we're looking for a relationship or an expression to describe the R mean. And where does it come from? It comes from this right triangle. Based on the known, based on the theta, to give you an expression. Okay. Can somebody actually now say this? So what would be an expression for R mean? Root 2 sine theta. Root 2 sine theta. Root 2 over sine theta. Yes, right. Sine theta equal to root 2 over R mean. So R mean equal to root 2 over sine theta. Okay, good. So that's the idea. Okay, so when you see a tricky region that doesn't give you a constant right away when you draw this the reading line. So then how would you find the expression for R mean? You're going to have to look for the given geometry, given region. Try to find some sort of a geometry that can make use of mostly using trigonometry to give you an expression of R mean here. Very good. So this is your R mean and this is your R max. Okay, now we're done with the step 1 to find the R limits. Then the next step is to find theta limits. So theta limits is to do that is you rotate the reading line you draw from the first step and sweep through the region R. So by doing that, basically what I mean is you're doing this. Okay, so it's like this is your how do I do rotation here? Sorry. Anyway, you know what I'm going to do. So basically, you're going to rotate from here. Well, that's not rotating. You rotate from this side to this side. Right? Obviously, you're going to find the two particular edges. Right? One is here, one is here, to sandwich the region R as you're rotating and sweeping through this region R at here. And the two edges, okay, the two edges will give you theta mean and theta max. Right, so theta mean are obviously is given by this edge, and theta max obviously given by this edge. So that's the second step. Rotate the reading line and sweep through this region R. You can either call it boundaries or edges, right? Will give you the theta mean and theta max. So let's deal with the easy one again, right? So this edge give you the maximum for the theta. Theta always reference to the x-axis. And always starting from axis, you draw counterclockwise. You draw counterclockwise to where the reading line is, and then corresponding angle is the theta. Okay. So if you draw the clockwise, then you actually will get a negative value. Okay. So in this case, theta max, okay, I think it's pretty straightforward. It's 90 degrees. And theta mean is given by this particular edge. So we need to find what is this angle here. So to find that angle, I mean, that arrow line passing through this point, right? So if I can find the coordinates of that point, then I'll be able to find the corresponding angle. So basically, this point is the intersection between the straight line and the circle. You already have the y coordinates, which is √2. You just need the x coordinates for this point. So how do I get that? You substitute y coordinate into the circle equation. You solve for x. So this particular point, you get it's a √2, √2. Okay, so you get x is equal to √2, y equal to √2. So that immediately will give you, so what do you think is the theta mean angle? 45, right? Yeah, pi over 4. Good. So this is your theta mean, theta max. So finally, you can fill in the information of the limits. So R goes from, right, as it says, R goes from √2 over sine theta to 2. And theta goes from pi over 4 to pi over 2. So if I have the function f, then I'll be able to calculate the rest of the integrals. Right? So this is the process, how to deal with a region, how to scan through a region under polar coordinates. It's still the same concept, scanning through the region R. Okay. Yes. Over here? You mean how I substitute the x and y over here? Oh, how I found this one here. Oh, okay. Right, yeah. So the point we're looking at is the intersection between this line and this circle. So this is a line, but it's a constant, y equal to √2. Then all you need to do is substitute y over here. So you get x squared plus √2 squared equal to 4. That's 2. 4 minus 2 is 2. So x squared equal to 2. So x squared, x equal to technically positive negative √2, right? Yeah. But however, this is in the first quadrant, so you're not going to take the negative value. So you just take the positive value. So for this particular point, its coordinate is √2, √2. Yeah. Is that good? Good. So let's go back to our example. Remember the example we didn't really solve, right? Using Cartesian coordinates. Okay, so let's solve the question. The function is 1 minus x squared minus y squared. And the region R is that quarter circle with a unit radius. This is your region R here. So now I'm going to calculate this using polar coordinates. Okay, so let's transform the function we're integrating into everything into R and theta. So you're replacing x with R cosine theta. You're replacing y with R sine theta. Here you have a very simple trig identity. So you got a cosine theta square plus sine theta square, which is 1. So you get 1 minus r squared. So your original 1 minus x squared minus y squared is 1 minus r squared. Okay. So then I'm integrating this function. I'm integrating this 1 minus x squared and then times r dr d theta. This is the setup for this double integral. Then what will be the integral limits? So let's use the approach we just exercised to find the r and the theta limits. The approach is starting from origin. You draw an arrow lines across this region R. First contact give you R mean, second contact give you R max. So first contact is already there on the origin. So first contact must be 0. Second contact really doesn't matter where you draw the arrow line, the reading line, it always falls on the circle. So R max, which is second contact, that's distance from origin to where the second contact is. So that gives you 1. Then you sweep this arrow line, sweep this reading line from one end to the other end, or from one edge from the other edge, and that gives you the theta mean and theta max. So the first edge is right on the x-axis, so theta must be 0. The second edge is right on the y-axis, and that must be pi over 2. Right, so that's the whole setup. So now let's calculate the integral. So now when you look at this integral, I think it's much less comfortable to calculate than the previous, which involves square roots, cube terms, square terms, right? Yeah. So for this one here, you can calculate the internal r here. So we get a 1 over 2 r squared minus 1 over 4 r to the power 4. Substitute 0 to 1 into it. Okay. So when r equal to 1, you get a 1/2 minus 1/4, so which is 1/4. When you plug 0 here, you get all zeros, so that's just 1/4. And theta, you're left with just d theta. So that's pi over 2. So you can basically end up with pi over 8. So you can see now, immediately see the benefit of transforming the original double integral from Cartesian coordinates into polar coordinates. Okay. The computation-wise, much less scary. So that actually begs the question is, then under what situation should I use polar coordinates? Or under what situation should you use Cartesian coordinates? So Cartesian coordinates technically is more generic. For any regions, you could use Cartesian coordinates, okay, under all situations. But for polar coordinates, okay, in most of the time, it's probably applicable when your region involve a circular edges. So like this case, right? So when you have a circle involved here, and like this case, you also have a circle, part of the edge or boundary is a circle, right, for the region R. So in those cases, you have better chance of getting an easier computation to use polar coordinates than Cartesian coordinates. Okay. So let's take a look at one more example here. Here's a boundary for the region R. Okay, here's all the necessary boundaries for you to sketch this region R. So once you have this information, I need you to be able to sketch that. As you can clearly see, there are two boundaries, which are two circles. The B is more than A, so one of the circle has a larger radius. And so you can draw two circles. And the other one is x-axis, and also y is more than 0. So you're only like looking at half of the circle, right? The top half. So if this is A, this is B. So your whole region R is like a half donut kind of geometry, right? That's your region R. Okay. So then let's see. Let's integrate the following double integral. Okay. So very straightforward. Just integrate the function is y. I mean, you can certainly try Cartesian coordinates. And I can guarantee if you try Cartesian coordinates, it's much complicated to calculate the integral. So if we use polar coordinates, as you can see, okay, it's much easier. So y, right, transform to polar, r sine theta, and dA is r dr d theta. Now let's look at the limits. Going to follow the process that we have done. Draw a reading line, okay, in the r direction. First contact, give me r mean. Second contact, give me the r max. In this case, r mean always on the inner circle, r max is always on the outer circle. So r mean must be A, r max must be B. Then you sweep this reading line to find the two edges. So one is over here, another one is over here, right? So theta mean is 0, and theta max is right here, so that's pi. So everything's done. Then you calculate this integral. It's a very simple integral to calculate this. As you can see, you get a 2/3 b cubed minus a cubed. That's a result of this double integral. Okay, good. So I'm going to stop here, and then we'll look at another concept called the general change variable. So what if you know, neither the polar coordinate or Cartesian coordinate is not going to work? What are we going to do, right? So we have to find an alternative solution. So we call it general change variable. So we'll talk to you on Friday. What for previous example, y r mean is 0 for the previous example. Because the contact already starts based on the origin, right? So that's why r mean is 0. The first contact point is right here on the origin. That's a question from online. Come in. Yeah.
Just a quick question, actually. I understand the math. I have no problem with that. But what I remember is the area of unit circle is pi, right? And you're just taking it 1/4, it should be pi over 4, like if you think about it as a unit circle. But we found pi over 8.
Well, first of all, the results are here, right? It has nothing to do with the area of the unit circle.
Yeah.
Okay.
But basically, you're thinking you're thinking it on n and x or xy.
Yes. So remember, you're integrating this function over this region R. So in other words, right, if I relate to the concept volume, so this function is on top of this. There's some surface on top of this part of this region R, right?
Yeah.
So you're calculating actually the volume based on this quarter circle, and then up to wherever that function is.
Yeah, something like, okay, gotcha.
Right?
Gotcha.
And
Okay,
in this case, it's a paraboloid. This is y minus x square minus y square, right? So it's a paraboloid hovering on top of this. Right? Can you imagine that? You know? Yeah. So that's what you get. The value pi over 8 is the volume above this and below that paraboloid.
Exactly. Yeah.
Yeah.
Okay, got it. Thank you so much.
Yeah. You're welcome. Yeah.